Thank you to those who joined early today again. Um, please get your calculators and notes ready today. It will be another day of just a lot of notes and a lot of problems. And yeah, let's just wait a couple more minutes so that everybody else can join. Okay, guys, let's wait 2 more minutes for everybody and then we'll get started. Please have your calculator and notes ready again. And make sure you write down everything you need on the slides today because you'll definitely be needing them for our practice questions. Yeah, let's wait another minute and then we'll get started today. Okay. Um, it is 10:32, so I will get started. Okay. So welcome back to Intro to Physics. Today is Thursday, so it'll be our last lecture day because tomorrow will be our final review day. Okay. So looking at our 2-week plan again, first week we covered basically what is physics, right? And basically like kinematics and started Newton's first law. Now it's our second week. So we finished Newton's laws, right? Adam talked a little bit about circular motion yesterday, but we decided to just move on to momentum, energy, and work. We thought that'd be a little bit easier for you guys. So that'll be the last thing we will be covering in our 2-week class, okay? And tomorrow will be final review day, obviously, where we'll just post like a Kahoot and etc. Okay, so here's today's agenda. So we have our introduction, and then I'll introduce some concepts to you guys. We'll do some practice questions, and then we will end with closing. Any questions so far? Nope. All right. Then I'll move on. Okay, so work, energy, and momentum. So start off with work, right? So in physics, work is defined as the transfer of energy that occurs when a force is applied to an object and the object moves in the direction of that force. So mathematically, work is calculated using the formula. So work equals force times displacement times cosine theta, right? So F d cosine theta, would, if you say it simplified, right? So F is obviously the magnitude of the force applied. D is the displacement of the object, and theta, that's the angle between the force and the direction of the motion, right? So if the force is in the same direction as displacement or where you're moving, our theta will be 0, and the work done will simply be the product of force and distance, but I'll get to that later on. And work is measured in joules, all right? So joules, and well, 1 joule equals 1 Newton meter, but that's not really important. Just know that work will be measured in joules, all right? It's important to know that not all forces do work, right? So if there's no movement, right? So if displacement is 0, or if the force is perpendicular to the direction of movement, then no work will be done, right? So one example is, let's say you hold like a heavy box, right? In place, it's not moving, right? So it does involve force, right? Because you're keeping it up against the force of gravity, right? But no work is done in the physics sense, right? Because your displacement is still 0, right? You're not moving the box, it's just staying still. So the work done is technically still 0, right? And it's important to know that work can also be positive or negative, right? So positive work, it adds energy to a system, like pushing a sled forward, right? And negative work removes energy, right? So like friction slowing down a moving object, right? So that's work. I'll stay on this slide for another minute or so you guys can copy it down. Okay. Um, I'm going to move on. Is anybody still copying the slides?
Yes.
Okay, yeah, I'll wait. I'll also be sending the slides to you guys after class. So if you don't get like a lot the last couple bullet points, then it's fine. You guys can copy it down when I give it to you. Okay, let's get the class. Okay. All right, I'll move on then. So next is energy, right? So what is energy, right? So in physics, energy is the ability to do work or cause change, right? So it exists in many forms, like such as kinetic energy, potential energy, thermal energy, chemical energy, and way more. We'll be mostly covering kinetic and potential energy in intro to physics. So again, energy, it's measured in joules, right? The same unit as work, okay? And yeah, we usually split kinetic energy into two general kinds for this class, intro to physics, with kinetic and potential energy. I'll stay on this slide for like 15 more seconds and then we'll move on. We do have a lot of practice questions to get to today, so let's try to move things along. Okay, so let's talk about kinetic and potential energy, right? So potential energy, so let's start with kinetic energy, right? So kinetic energy, it's the energy of motion, right? So any object that is moving will have kinetic energy, right? And kinetic energy depends on both its mass and velocity, as seen by the formula, right? So the faster an object moves or the more mass it has, the more kinetic energy it will have, right? The formula to calculate kinetic energy is Ke, which stands for kinetic energy, right? Is 1/2 mv squared, right? Where m will be the mass of the object and v is the velocity of the object, right? So for example, let's like compare like the changes in mass and velocity, right? So if you have a rolling soccer ball or like a speeding car, they both have kinetic energy, right? And if their speed increases, their energy will drastically increase since velocity is squared in the formula. So for example, let's say we have a car and its mass is 2 kg, right? If it's 2 kg, right, and its velocity is, let's say it's 2 meters per second, right? Then if we use the formula, if we plug it in, right, 1/2, and which is 2 times 2 squared, right? Because that's the velocity, we get 4, right? As our kinetic energy, right? 4 joules. But let's say velocity was 4 meters per second, right? Then we do the same thing, but since 4 is squared, our energy drastically increases, right? Just by changing our velocity, right? If we change mass to, let's say, be 4 kilograms, then our value wouldn't change as much. It would be closer to 8 joules, right? So I think it's obvious, but if you square a value, it grows greater, right, than just having it. And next will be potential energy, right? So potential energy, on the other hand, it's like a stored energy based on like an object's position or condition. So the most common type you'll see in Intro to Physics and AP Physics 1 will be gravitational potential energy, right? So that depends on an object's height above the ground, right? And our formula is PE, so potential energy equals mgh, where you already know mass and gravity, and h is the height above the ground, right? So a rock being held at the top of a cliff, right? So that has gravitational potential energy, right? Because it has a height, right? And when that rock is released, right, that energy will be converted into kinetic energy, right? So when a ball falls from a cliff, its potential energy will decrease while its kinetic energy increases, right? But the total energy of the system will stay constant. So if you have a ball at the top of the cliff, you drop it, right? Its height decreases, right, as it's falling, right? So its potential energy will decrease, right? Because mass and gravity stays constant, right? The height is changing, right? But as you're dropping, velocity of the ball increases, right, as you're dropping, right? And remember, kinetic energy is 1/2 mv squared, right? So as gravitational potential energy decreases, kinetic energy will increase, right? So just make sure that in a closed system, the total energy will stay constant, okay? And in my example, this is assuming that there's no air resistance, right? In a closed system, no external forces. Okay, there's a lot of text on this slide. I'll stay on this for another couple seconds. Does anybody have any questions regarding kinetic and potential energy? No. Or is anybody still copying the slides down? Okay, I'll wait another 30 seconds. I'll start a timer, but if you don't get it again, I'll send the slides out. Okay. It's been 30 seconds. If you didn't get it again, I'll send the slides over, so don't worry. Okay, let's talk about the work energy theorem, right? So this is related to energy, right? So the work energy theorem states that the net work done on an object is equal to the change in its kinetic energy. So in other words, when a force causes an object to move, the energy used to do that work goes into changing the object's motion, right? So mathematically, it's written as W. So say work, right? Work is the change, like delta KE, right? Change in kinetic energy, right? So that will be 1/2 mv squared final minus 1/2 mv squared initial, right? So that's final velocity and initial velocity, right? W is going to be the net work done. And again, delta KE is the change in kinetic energy, right? So that means if you push an object at rest and then it starts moving, the work you did becomes its kinetic energy, right? So this theorem can be useful because it links the concepts of force, motion, energy, right? And let's say, to give an example, right? If a car speeds up, the engine must do work on the car, right? Which increases its kinetic energy, right? If a car slows down, the work is done against the car's motion, right? So just let's say by like the brakes in a car or by friction, right? And that results in a decrease of kinetic energy, right? Because velocity decreases. So the work energy theorem, it kind of helps explain how energy is kind of transferred and transformed through different physical interactions. Okay, yeah. I'll write all the variable names, right? So this will be work, let's just, W will be like network, okay? Um, delta KE is change in kinetic energy. Okay, and M is mass, V is velocity. And once again, you're subtracting, you're basically subtracting initial from final, right? So your final velocity minus initial. Yeah, I'll stay on this side again, another 30 seconds, then yeah, we'll move on. Okay, let's move on to our next slide. Okay, let's talk about the law of conservation of energy, right? So the fundamental principle in physics, and you may have heard it in other classes as well, but this basically states that energy cannot be created or destroyed, right? It can only be transformed from one form to another or transferred between objects. So this means that the total amount of energy in a closed system remains constant over time. So closed system, right? So we're excluding like friction, air resistance, right? So closed system, okay? So let's say to give an example, right? A roller coaster, right? Let's say it descends from a really high point, right? Its gravitational potential energy, it becomes kinetic energy, right? As it speeds up, as it goes down the, say, track, right? But the total amount of energy will stay the same, okay? Because there's gravitational potential energy plus kinetic energy in a closed system, right? That equals the total energy in a system, right? So if gravitational potential energy decreases, kinetic energy will increase that same amount to keep the total amount of energy balanced, right? So, and we call that basically mechanical energy, right? Them combined together. And this principle kind of explains many kind of, let's say, everyday phenomena, right? So let's say like we have a swinging pendulum, for instance, right? So that constantly shifts between potential energy and kinetic energy, right? Because you can have a pendulum, this string, right? You have a ball, right? It basically swings back and forth, right? And at this highest point, its gravitational potential energy will obviously be the highest, right? But at this middle part, that's when its kinetic energy will be the greatest, right? So, but the total amount of energy, the mechanical energy in the system will remain constant, right? Um, in some most real life situations, some energy kind of transforms into thermal energy due to friction, right? But even then, energy just isn't lost, right? It's just changing form, okay? So, but in our class, let's just stick to closed systems and basically kinetic energy and gravitational potential energy, right? So understanding the conservation of energy, it's crucial for solving physics problems, right? Because you need to understand that no energy is lost, right? It's always transferred or transformed, right? Okay. I will give another 30 seconds for this. Okay. I think there's still some people copying down the slides. Okay, I will have to move on so we get to all the questions, okay? Yeah, let's talk about momentum now. Okay, so what is momentum, right? So momentum, it's a measure of how much motion an object has and how difficult it is to stop it, right? So in physics, momentum is defined as the product of its mass and velocity. So it's represented by the formula P equals mv. So P is momentum, right? So P is momentum, M is mass, and V is velocity, okay? Because velocity is a vector, momentum will also become a vector, right? So it also has magnitude and direction, okay? And the units of momentum are kilogram meters per second. And basically, the more mass or speed it has, the more momentum an object has, right? I think that's kind of easy to visualize, right? If you have a heavier car moving, then it will have more momentum and it'll be harder to stop it, right? So that's really it for momentum. Our next slide will be on the law of conservation of momentum, just really similar to the energy one, but it's a little bit different, uses some different formulas. Okay, I'll give another like 15 seconds and then we can move on. Okay, if you didn't get it all down, no worries. You'll be getting the slides after anyways. Okay, let's talk about the law of conservation of momentum. Okay, so this basically states that the total momentum of a closed isolated system will remain constant if no external forces act on it. Just really similar to the law of conservation of energy, right? So in other words, momentum before an interaction equals momentum after, right? So as long as nothing from outside the system interferes, right? Um, the formula says total momentum equals total momentum after. So usually this is written as m1v1 plus m2v2, yeah, m1 initial, v2 initial, these are all initials, is equal to m1 final, v1. Usually it's only the velocity that changes, right? But plus m2 v2 final. Okay, so let me erase this. Okay, the mass doesn't ever change, right? It's only the velocity that's changing, okay? So this is I, right? And that's F. So it'll be M1 V1 plus M2 V2 equals M1 V1 F plus M2 V2 F. Okay, so basically what it says is that your total momentum will remain the same, right? So the initial velocities of each object, they'll be equal to each other after the collision, right? So a common example is when two ice skaters push off each other, right? Let's say both of them are initially at rest, right? And then they push apart, okay? So one skater moves in one direction and the other moves in the opposite direction, right? But the total momentum will remain zero, right? Just as if they were before as they pushed off, right? When they weren't moving, right? So eventually their momentum it'll always stay zero. Momentum will always stay zero. And this law also applies to like car crashes or like rocket propulsion, right? Even when objects like bounce off each other or stick together, as long as there's no like outside force like friction, let's say, or air resistance, their combined momentum will stay the same, okay? So just know that the total momentum of a system will always remain constant if it's in a closed isolated system and there's no external forces that are acting on it. Okay, give another 30 seconds for this. Okay, I'll move on to our last lecture slide. Okay, let's talk about impulse. Okay, so what is impulse, right? So impulse is a change in momentum of an object when a force is applied over a period of time. So it's defined as the product of force times time. So it's given by formula impulse, which we represent using J equals force times time, or delta T, right? So impulse, it's also equal to the change in momentum as well. So it can also be written as J equals delta P, or like change in momentum, which will be M times change in velocity, right? So in often cases, what we'll have to do, right, is start with J, right? So J equals force times delta T, right? But impulse, right? Impulse also equals change in momentum, right? So in many cases, we're going to have to use two of these values, sorry, two of these equations to find out what we need, right? So it's just important to know that impulse, it's fine using force times delta T, or it's also known as the change in momentum, right? And since impulse, since it's a change in momentum, right? Impulse also shares the same unit as momentum, right? If you remember, that's kilogram meters per second, or it can be written as Newton seconds, right? Um, Impulse is important in situations where forces kind of act for short durations, like let's say like in collisions or like sports, right? Say when a baseball hits a ball, right? The bat applies a large force over a small amount of time, right? Giving the ball a sudden change in momentum, right? And increasing the time over which a force acts, right? Such as following through on the swing, right? Like can reduce the impact force while still delivering the same impulse, right? So this relationship between like force, time, and momentum, right? It's like a key concept, like especially in like sports, right? Especially for baseball, right? When you need to send the ball as far as you can, right? With the most momentum you can, with as much momentum as you can, right? So yeah, this is our final lecture slide, and then we'll get to some practice questions after this. If you're running out of running out of time to copy things, just make sure you get this. Can okay. Um, is anybody still copying anything down from this slide? Nope. All right, great. I'll move on. Okay, so here are all the important formulas that we covered today. So if you didn't get any of these, or you just want to write down like a section like important formulas, here it is. So we have work, right? So work is force times displacement times cosine theta. Kinetic energy, which is 1/2 mv squared. Potential energy, which is mass times gravity times height. Momentum is mass times velocity. Impulse is force times delta T. It's also equal to the change in momentum. And our work energy theorem, just the kinetic energy final minus initial kinetic energy, right? So we'll just write. Okay. I think you should have most, if not all of these kind of memorized, right? like what each of these symbols mean. Right, so in case you didn't know what any of these symbols meant, right, here it is. Um, I'll actually stay a bit longer on this side so you guys can get everything down. It's going to be pretty important for slides coming up, okay? Okay, does anybody need more time copying down these slides? Okay, okay, all right, I'll give 20 more seconds max, okay? Okay, let's get to some problems. Okay. If you already know these or you have them written down, I mean, there's no need to copy these, right? So just copy down the things you don't know. And all right, so let's get moving to our next slide. Okay, let's do some practice questions now. Okay, so the first one, a person applies 20 Newton force to push a box 5 meters. So how much work is done on the box, right? I'll give you guys say 20 to 30 seconds for this, and then one person could maybe explain how they solve this question. So yeah, I'll set a timer for 30 seconds, and then if you guys could put your answers through the chat, or you can raise your virtual hand, then I can call on you. You can tell me how you got your answer. Okay, it's been a while. Do you guys need more time on this question? Or, okay, oh wait, you guys are solving both of them. Okay, yeah, okay, wait, let's do the first question first, right? Okay, think, yeah, okay, some people have solved it correctly, so I'll go over it. Only some people have responded, so let's see our first question, right? 20 units of force to push a box 5 meters, right? So work, right? Work equals force times displacement times cosine theta, right? Okay, so our force is applied horizontally, right? And since the motion is also horizontal, our angle will be theta will become 0 degrees, right? It's not applied at any degree to the horizontal, so this will be 0, right? Oh yeah, so you guys might not know this, but okay, cosine of 0 is 1. And cosine of 90 is 0. You guys, I won't explain how we got that, but just keep in mind, cosine of 0 is 1, cosine of 90 is 0, right? That might have confused you guys or like got you guys stuck, right? So all you gotta do is work equals force, that's 20 newtons, right? Times 5 meters times 1, since cosine of 0 is 1, you get 100 joules, right? That's how much you got. Okay. Yeah, let's move on to the second question, right? So a force of 50 newtons is applied at an angle of 60 degrees to the horizontal. The object moves 10 meters. What is the work done? Okay. Okay, remember, this is the same work formula. Um, just keep in mind. So if you have your calculator with you, yeah, definitely use your calculator for this, unless you have taken trig in middle or high school. Okay, I'm seeing some answers. Okay, yeah, great. Okay, yeah, I'm seeing a lot of correct answers. So, yep, work again, FD cosine theta, right? So force is 50 newtons, it moves 10 meters, cosine 60, right? This is what I need to do. Okay, if you've taken trig, which I assume most of you haven't, it's coming on, but you can use your calculator for this, right? So cosine 60 is 1/2, okay? So it's just 50 times 10 times 0.5, right? Times 0.5, right? So this will be 500 times 0.5, which is 250 joules, right? Yeah, I think some of you have gotten that. That's great. Yeah, this is a lot of just plugging in and getting your answers, right? Some of my teachers just say plug and chug, right? If you have your values, just like plug them in and get your values, right? Okay. Um, on to our next slide. Is anybody still like copying down or working on this? Nope, all right. Okay, let's do this. Okay, so a 3 kilogram ball rolls at 4 meters per second. What is its kinetic energy? Okay, I think this is also another question that's really doable for you guys. Just plugging and chugging, right? I'll give 30 seconds for this. Okay, just in case you don't have the formula. Yep, again, you can put your answers to the chat or raise your virtual hand. Okay, yeah. Okay, yeah, everybody has answered so far got it right. So just solve it again for those who are able to solve it right. KE, just plug in 1/2. What's our mass? 3 kilograms. Okay, 3 times 4 squared, okay? Because that's our velocity. So this will just be 3 halves times 16, right? Just again, if you use the calculator, 24 joules, right? So that's our kinetic energy of the ball. Okay, this is just using the formula and just plugging in values to get your answer, right? Okay, let's do the second one. Also, a 5 kilogram object is held 10 meters above the ground. What is its gravitational potential energy? Okay, remember formula, potential energy, mgh, right? Again, give you guys another couple seconds to solve this. And put your answer through the chat. Okay, how do you get one person to answer this? Okay, Jaden, you got this question correct. How did you solve this question? Can you explain it to me?
So the mass is 5 kilograms, and then the height is 10 meters, and gravity is 9.8. And if you just multiply it all, you get 490.
Yeah, 490 what? What are your units? Okay, okay. So yeah, what he said, right? Mass is 5 kilograms, height is 10, gravity is 9.8, right? So we just multiply these together, get 490, right? And joules. Okay, so it's important to include your units, right? So energy is in joules, right? So it can't be 490, right? So it has to be 490 joules. Okay. Okay, that was also another pretty simple question. Okay, let's move on to our next slide. Okay, an object has 200 joules of potential energy and weighs 100 newtons. How high is it above the ground? Okay. This might be a little bit tricky, but I'll give you guys another like 30 seconds to solve it, okay? This involves a little bit of kind of substitution. I'm seeing, okay, less answers. Okay, far more incorrect ones as well. Okay, I'll solve this one, okay? So it's a little bit tricky. Okay, so this is what we know, right? Potential energy equals mass times gravity times height. It tells us it weighs 100 newtons, right? Weighs 100 newtons, right? So notice the units, right? It weighs 100 newtons, so it's not grams, kilograms, right? It's force, okay? You guys might remember that weight is mg, okay? So what we need to do is this is the weight force, okay? So the force of weight, okay? So if you plug in 100 newtons for this, you'll get this wrong, or like 100 grams, let's say. For mass, you'll 100% get this wrong, okay? So we're given that this is 100 newtons, okay? It's a little bit tricky, okay? So what we need to do is it's just potential energy, which are actually given, okay, right there later. So it's W equals mg, and we're given that it weighs 100 newtons. The force of weight is 100 newtons, right? Just 100. Whoa. Okay, no, what that was 100 times h, okay? And potential energy, 200 joules. Okay, 200 plus 100 times H. And H will be 200 over 100. So H equals 2 meters above the ground. Okay, so this question, right, I think it was a little bit tricky, right? Because it weighs 100 newtons. We're not given it in like regular like grams or kilograms, right? So that's when we need to identify that weight equals mg, right? And we covered that thing last week, right? And we just plug in for 100 newtons, right? All right, let's move on to our second question. An object starts at rest and has 800 joules of work done on it. What is its final kinetic energy? Okay, so again, I'll give you guys a couple seconds to solve this. Slightly more conceptual than calculating this one. Um, yeah, I think I will have to explain this one. It's a little bit tricky. Okay, so remember, okay, I actually got it. Okay, yeah. So it starts at rest and has 800 joules of work done on the object, right? So let's use the work energy theorem, right? So remember, that means work done equals the change in kinetic energy, right? That is final kinetic energy minus K initial kinetic energy, right? And it starts at rest. An object at rest has no kinetic energy, right? Because velocity is zero, remember. Ke equals 1/2 mv squared. If v is zero, the whole thing is zero, right? So what this means is it has 800 joules of work done on it, right? So it's just 800 minus zero. So it's final kinetic energy, right? So it will be 800 joules, like some of you guys have said, right? Okay, great. So this is a little bit conceptual, right? Understanding that at rest, there is no kinetic energy, right? It's zero, right? Because velocity is zero and it has 800 joules of work done on it. So oh wait, okay, yeah, actually, I did this incorrect. Okay, so we need to find for final kinetic, right? And this is zero. Will actually be 800, right? Because it says it has 800 joules of work done on it, right? So KEF will be 800 joules, my bad, I'm sorry. Because we need to find for final kinetic energy, right? So it will be 800 joules, same answer, but yeah. All right. Um, I'll move on to our next slide. Let's look at this question. Okay, so a 1,000 kilogram car goes from 5 meters per second to 15 meters per second. How much work is done on this car? Okay, this will be work energy theorem again. Okay. Okay, I'll give you guys again time to solve this question. Okay. Not getting chances. Okay, let me give you guys a bit longer. This does require a calculator. Okay, let's help this actually. Okay, so what is kinetic energy, right? Kinetic energy, 1/2 mv squared, right? And this is our change in kinetic energy, right? So this will be 1/2 mv your final velocity squared minus 1/2 mv initial squared, okay? And we have all the values we need, right? So this is just 1/2 times 1000, right? So that's our mass, right? 215 meters per second, that's our final velocity. Okay, parentheses. When we subtract it over 1/2 times 1000 again, but this time it will be our initial velocity squared, right? So 5 squared, okay? You can put this into the calculator, but this will eventually equal, I'm pretty sure, to 100, 100,000, it'll be 100,000 joules. Okay, yeah, this one, what we did is, it's just work, right? Changing kinetic energy. Kinetic energy is 1/2 mv squared, right? So we subtracted initial from our final because we were given both initial and final velocity, right? Okay, so our next question is 0.2 kilogram baseball is thrown at 40 meters per second. What is the ball's momentum? It's a bit more simple than our last question. Remember, momentum is mv. Okay, yeah, I got a question. How do you spell joules? Okay, so J, right? Spelled like this. Joules. Ojoules. Okay, yeah, what is its momentum? Right, I think some of you got it right. P equals, it will be 0.2 times 40. What is this? 8. Okay, but units for momentum, not joules. Momentum is not in joules. It's in kilograms times meters per second. Okay, so just understand energy is in joules, momentum is in kilograms per meters per second. Yeah, some of you guys may be confused by units, but yeah. Momentum is kilograms times meters per second. I think that was in the slides before, but yeah. Okay, I'll move on to our next slide. Okay, which has more momentum? A 0.05 kilogram bullet traveling at 500 meters per second or a 1,000 kilogram car traveling at 0.03 meters per second, okay? So this will be double calculations and comparing these, right? Remember, just in case you forgot from what I wrote 30 seconds ago, momentum is mass times velocity, right? So what has more moment? Okay, I'm seeing some answers, and yeah, they are correct. Okay, so let's solve this, right? So let's solve for the bullet first, right? 0.05 times 500, right? That would be 25 meters per second. You can do the car also, just 1000 times 0.03, so equal 30, right? So as some of you guys have said, the car has more momentum. Car has more momentum. Okay, we just compared both of them, and we know that 30 is greater than 25, so that's how we got our answer. Okay, yeah, all I had to do is just multiply mass by velocity, right? Okay, let's just solve this final question, then we'll end class today. There are more practice questions at the end of the slides, so you guys can solve them when I send them to you. Okay, a force of 10 newtons acts on a ball for 2 seconds. What is the impulse? For J, which is this, impulse is signified as J, okay? So, let's see. Just solve this question, last question. I'll give you guys a couple seconds to solve it. That's a T, guys. Okay. If you guys are confused, okay, I'll just write T like this. Okay. It's delta T, right? Um, okay. I'll solve this again. Like some of you got J. Force is 10, time is 2. Great. That's our answer, newtons per second. That's our units per impulse, right? It can also be written as kilograms meters per second, but we usually use newtons times seconds for impulse. Okay, so that will be the end of our final lecture day today. We had more slides, right? We had more practice questions. There are some pretty good ones, so if you guys want to solve them, you guys are free to do that. But thank you for joining me and Autumn today on our final lecture day. Tomorrow will be a review day where it's mostly you guys are going to be solving Kahoot questions, right? So that's it for class today. You guys are free to leave now. All right, thank you for joining us. If you have any questions, you can stay behind after class.
Thank you. Bye.
Yeah,
Thank
bye.
you. Bye.